All right, so rate calculations. Looking at the ones that we saw in the video, remember our first step was we need to go through and we need to figure out or be able to write these reaction rate expressions based on the balanced chemical equation. And so we're going to start with a problem just like that, where we're going to have a balanced chemical equation, reaction between nitrogen gas and oxygen gas to produce two molecules of NO. We're going to write the rate expression in terms of both of all three, nitrogen, oxygen, and nitrogen monoxide. And so we start by saying essentially we're writing the rate expression, so the reaction rate is going to be equal to, right? And remember, it's concentration of change in concentration over change in time, and then we have to take into account the stoichiometric factor, and we have to take into account whether it's on the left or the right hand side of the equation. So if we're going to look at nitrogen first, it would be the change in the concentration of nitrogen over the change in time. Because it's a reactant and it's disappearing, it's going to have a negative sign. And remember that what we want to do is we have to take into account the stoichiometric ratio. So we're going to multiply by a fraction of 1 over 1. 1 over whatever the stoichiometric ratio would be, the stoichiometric coefficient would be. For oxygen, it's going to be similar. It's going to be the change in the concentration of oxygen over the change in time. It's going to be negative because it's a reactant and it's disappearing, and it's going to be multiplied by 1 over 1, where the denominator 1 comes from the balanced chemical equation. Now the nitrogen monoxide, it's going to be appearing. It's a product. It's going to be produced, so it's going to be appearing. It's going to have a sign of positive, and it's going to be the change in the concentration of nitrogen monoxide over the change in time, and it's going to be multiplied by a factor of 1 over 2, where 2 is a stoichiometric coefficient from the balanced chemical equation. So if we'd write this out a little bit more cleanly, this would be minus delta concentration of nitrogen over delta time, change in time. It would be minus change in concentration of oxygen over change in time. And that would be equal to plus 1/2 change in concentration of nitrogen monoxide over change in time. Those would be the expressions for the reaction rate of this particular reaction. Now the next problem, and again, the way that this works is when you see the problem, pause it and try it on your own, especially these next couple, because they're going to be very similar to the one that we just did. So what's the rate expression in terms of ethanol for this particular reaction? And that's what we want to determine. So maybe pause the video, try to do the calculation on your own, then unpause it and come back to see how I work it. So the rate of this reaction, C2H5OH ethanol, is a product. Products appear or are appearing, so it's going to be positive. We're going to have the change in the concentration of methanol or of ethanol, C2H5OH, over change in time, and that's going to be multiplied by a factor of 1 over the stoichiometric coefficient in front of that particular compound. That's it. That's the rate expression in terms of ethanol. All right? Now, the next problem is going to be dealing with what's the overall reaction rate expression. What's the overall reaction rate expression for this chemical reaction? And this is just going to be very similar to what we just did, except when we're writing overall reaction rates, we always choose the reactant or a reactant that has a coefficient of 1 in front of it in the balanced chemical equation. So in this case, if we're going to write the overall reaction rate, we're going to write it in terms of the reactant with a coefficient of 1 in front of it. So we're going to write it for the glucose here. So first of all, it's going to be negative, okay? Negative change in concentration of glucose, C6H12O6, over change in time, and it's multiplied by a factor of 1 over 1, where the denominator 1 comes from the balanced chemical equation. So if we wrote this a little more cleanly, it would be negative the change in the concentration of C6H12O6 over the change in time. And that would be normally what we'd consider the overall reaction rate. I just want you to be familiar with that terminology and how to find that if that would be something that would come up. All right, so I'm sorry, I'm one step ahead. We were talking about the idea of, talking about the idea of average versus instantaneous reaction rate. And where we said we could first find the average reaction rate. All right, first we have this line, this curved line, which represents the changing concentration of the analyte versus time. Then we have this straight line, and the straight line represents the average rate of change between time equals 0 and time equals 4. And the slope of that line is going to tell us what the average reaction rate will be between those two times. So we're going to do that, and we're going to do the same thing, or do something similar to that, perform a calculation like this, except instead of having to look at the plot, you actually have a table of data. And the table of data is telling you over time, between time equals 0 and time equals 4, what the concentration of this ICL compound would be. And so we want to look at the average reaction rate for the disappearance of ICL between 1 and 4 seconds. So the first step here is going to be that we're going to have to write the average rate, the rate expression for the disappearance of ICL. And then we're going to use that and use this data in this table to calculate what the rate would be. So the rate of change, or the reaction rate in terms of ICL, it's going to have a negative sign in front of it. It's going to be the concentration of ICL, the change in the concentration of ICL over the change in time, and it's going to have a factor in front of it of 1 over the 2, where the 2 comes from the coefficient in the balanced chemical equation. And if we're going to write this out, instead of just saying change in ICL and change in time, and we were going to do the initial versus final, this would be the same as saying minus 1/2 times the concentration of ICL final minus the concentration of ICL initial over T final minus T initial. And we're going between 1 and 4 seconds, so the initial is going to be at time equals 4, or time equal 1, sorry, and the final is going to be at time equal 4. And so that immediately tells us what T final and T initial would be. So I'm going to go ahead and start to write this out and say, okay, I know the denominator of this is going to be T final is 4 seconds, and T initial is 1 second. All right, now we just need to plug in the concentration. So at t equals 4, you get 0.75 minus t initial, the concentration at t initial, t equals 1, or 1.4. And whenever you plug that into your calculator, don't forget to factor in the minus 1/2. So when you plug that into your calculator, you find that the average rate of reaction between t equals 1, between 1 and 4 seconds, is 0.1083. What are the units? Well, these are in molarity in the denominator is in seconds, so it would be molar per second.